In this video, I am going to explain the role of 0, the role of 1 and distributive property of multiplication over addition and subtraction. So here, when you take any whole number and add 0 to it, you know that you get back the same number, right? So that is the example they have given here. And if you take any integer and add 0 to it, you know that you will get back the same number that you have taken, right? And if you take any rational number and add 0 to it, then you will get back the same rational number that you have taken, right? Now this number 0 is called the additive identity. Okay, so additive identity is nothing but an element which when added to a given element of a set, you get back the same number. Additive because the operation that we are talking about here is plus. Identity because even after performing the operation, you are getting back the same number or same element that you have taken, right? So 0 is the additive identity for the set of whole numbers, for the set of integers and for the set of rational numbers. Here I would like to ask you one question. Is it the additive identity for the set of natural numbers? Okay, think about it. Now here they have generalized it for any a. Whenever a is a whole number, a plus 0 is equal to 0 plus a is equal to a. Whenever b is an integer, b plus 0 is equal to 0 plus b is equal to b. Whenever c is a rational number, c plus 0 is equal to 0 plus c is equal to c, right? But that is adding 0 from both directions. Either way, you are getting back the same number that you have taken. So 0 is called the identity for addition or additive identity for all these three sets. Next, coming to the role of 1. Now whenever I multiply any whole number by 1, what do I get? I get back the same number again. Whenever I multiply any rational number, minus 2 by 7 is a rational number. Whenever I multiply any rational number by 1, I get back the same rational number, right? This is also a rational number, 3 by 8. I am getting back the same number, right? So here 1 is called the multiplicative identity, right? What do we mean by multiplicative identity? Whenever this identity, multiplicative identity is multiplied by a given number, you get back the same number. Multiplicative because you're talking about the operation multiplication here, and identity because even after performing the operation, you're getting back the same number that you have taken, right? So here we have concluded that 1 is the multiplicative identity for rational numbers, and then they are asking you, is 1 the multiplicative identity for integers and for whole numbers? The answer is yes. You can check for any integer and whole number. Whenever you multiply it with 1 in both directions, that is important. That is, take any integer minus 5. You have to multiply it minus 5 into 1 and check 1 into minus 5 also. Both ways you should be getting minus 5. If that holds true for all integers, then it is a multiplicative identity, right? So the answer is yes. Now here again I want you to think about it for natural numbers as well. Okay. Now coming to the next question, I want you to read it carefully. They are asking us, if a property holds for rational numbers, will it also hold for integers and for whole numbers? Which will and which will not? Okay. Now let us look at this question. We are talking about a property. What are the properties that we have learned? We have learned closure property, commutative property, and associative property, right? Okay. Now the question is, if any of these properties holds for rational numbers, can I conclude that it holds for integers and whole numbers as well, right? Now let's start with associative property. Now we know that associative property for the operations addition and multiplication, okay, you know that addition and multiplication are associative for the set of rational numbers. Can I conclude that addition and multiplication are associative for the set of whole numbers and integers as well? As we have already seen, you know the answer is yes, right? Right? Now, for commutative property, let us check. We have seen that addition and multiplication are commutative for the set of rational numbers. Okay. As a result, can I conclude that addition and multiplication are commutative for the set of whole numbers and integers? The answer is yes. You have seen that for the set of whole numbers and integers also, addition and multiplication are commutative, right? Now coming to closure property, you will see that closure property for the set of rational numbers, addition, subtraction and multiplication, all these three are the set of rational numbers is closed under all these three operations. For division there was an exception of the element 0, right? But you know, we have already seen that the set of whole numbers is not closed for subtraction, right? For addition it is closed, for multiplication it is closed, but subtraction it is not closed. Now if you look at integers, for addition it is closed, for subtraction it is closed, and for multiplication it is closed. Here there is only one problem, that is with the subtraction, right? So the set of rational numbers being closed under subtraction does not give us the conclusion that the set of whole numbers is closed under the set of whole numbers is closed under subtraction, right? Now why is this happening? The question is why. Actually they had stopped at which will be which will be holding true, which will not. That is commutative and associative properties, you can infer that. For closure you cannot infer. That is your answer. I want you to think one step ahead, that is why is it not possible for me to conclude, use the same logic for closure property. Now here, for the sake of this, I want you to look at these sets using Venn diagrams. Okay. Now this is the set of natural numbers. Okay. Then I am going to take the set of whole numbers. I have just added one element 0 here, and then I am going to take the set of integers where I have added the negatives of all the natural numbers, and then I am going to come to my rational numbers. Now here what I have done, I have taken all the numbers in the form p by q, where p and q are integers and q is not equal to 0. Now if these represent our sets that we have been discussing in this chapter, if you look at the associative and commutative property, the nature of that property is more to do with the operation itself rather than the set, because here the sets we are considering are simply, the set of integers is a subset of rational numbers, the set of whole numbers is a subset of integers, and the set of natural numbers is a subset of whole numbers. So these two properties are more about the operation that you are talking about, the mathematical operation, right? So if a mathematical operation is behaving in a certain manner for the set of rational numbers, then you can conclude its behavior for the subset, which is the integers or the whole numbers, or even for the natural numbers, right? Okay. Now coming to closure property. Now what is the definition of closure property? Here we are talking about if you have any two elements belonging to a set, okay, belonging to a set S, then A operation B, will it belong to the set or will it not belong to the set? This is what we are talking about. This is what we are interested in when it comes to closure property. So closure property is more about the result of an operation being performed, whether it belongs to the set or it does not belong to the set. So this is more about an element belonging or not belonging to the set, right? So if an element belongs to a superset, that is a larger set, can I conclude it always belongs to a subset? Suppose there is an element A here, right? A belongs to the set of rational numbers. Can I conclude A belongs to a set of integers? I can't conclude, right? So the reason why this logic is not working for closure property and it's working for commutative and associative property is that the nature of closure property is about an element belonging to that set, and because it is about an element belonging to a set, we know that an element belonging to a larger set does not guarantee that that same element belongs to the subset. That is kind of, that is the reason why you cannot conclude for closure property that if the rational numbers is closed under subtraction, I can't conclude that whole numbers are also closed under subtraction, right? So next, moving on to the next topic, that is our distributive property of multiplication over addition. Here I would like to add over addition and subtraction. Actually it is true for subtraction as well, right? Subtraction for rational numbers. Now what do we mean by distributive property of multiplication over addition or multiplication over subtraction? So here this is what it is, right? So if I have three elements belonging to rational numbers, for all rational numbers A, B, C, A into B plus C is equal to AB plus AC, and A into B minus C is equal to AB minus AC. Now this is our distribution of multiplication over addition and subtraction. That is, I can open the bracket and then simplify it. I will get the same answer, still get the same answer when I do it, right? So here they have given a solved example where they have done it for us. They have taken three rational numbers, minus 3 by 4, 2 by 3 and minus 5 by 6, and they have done A into B plus C. Okay, they have got some answer, and then they are doing A into B plus A into C, and then you will see that they will get the same answer in that manner as well, right? So they have given to try these questions. Okay, let's quickly solve these questions. So the first one is A into B plus A into C. I am going to write this as A into A is 7 by 5 for me here, A into B, which is minus 3 by 12, plus C, which is 5 by 12. Okay, now this is 7 by 5. This is the try this question. Okay, so I'm going to get 7 by 5 into, here I have the same denominator, I can simply add the numerators. This will give me 7 by 5 into 2 by 12, which on simplification is going to give me 7 by 30, right? So this is the answer for the first question. Next question. Again they have given AB plus AC. I am going to write it as A into B plus C. Okay, just like we have done in the earlier case. I am going to write it as this, where I'll get 9 by 16 into, now I have to take the LCM of 12 and 9, or before taking the LCM, if I were to simplify this, I am going to get 1 by 3 here and 1 by 3 here, and 1 by 3 minus 1 by 3 is 0, so the answer is going to be 0 here. So you can see here clearly that by using the distributive property, our calculations have become very easy. Now coming to the example, third example. Here again they have given us 2 by 5 into minus 3 by 7 minus 1 by 14 minus 3 by 7 into 3 by 5, right? So now here what we are doing is, these are the three elements we are talking about, right? Now we will be using the properties that we just learned to make our calculations easier. So what we will do is, you will notice that I have minus 3 by 7 here as well as here. So what he is doing is, he is going to bring minus 1 by 14, shift the place and bring this term minus 3 by 7 into 3 by 5 to the second place. Okay. Now after doing that using commutativity, right, here for shifting these to a plus b is equal to b plus a, he has used the commutative property, right? Now what we will be doing is, we are going to use minus 3 by 7 as a common and take it outside. Here you are using distributivity. So you are taking minus 3 by 7 outside, and then you will be left with 2 by 5 and 3 by 5 inside the bracket, right? Now when you solve this, because the denominator is common, you are going to get 1, and then you are getting minus 3 by 7 minus 1 by 14, the LCM is 14, so the answer is minus 1 by 2. Now by using the commutativity and distributivity, we have got the answer very quickly, right? So this is how the properties that we just learned are going to help us in solving the simplifying the mathematical expressions. Okay. Now coming to the exercise, we have 3 sums here. Now the first question is, name the property under multiplication used in each of the following. Now minus 4 by 5 into 1 is equal to 1 into minus 4 by 5 is equal to minus 4 by 5. Now here what is the property that is being used? Multiplicative identity, right? So here the property is multiplicative identity. Okay. Next, coming to the next question, minus 13 by 17 into minus 2 by 7 is equal to minus 2 by 7 into minus 13 by 17. What are we using? A into b is equal to b into a. You are using commutative property. So commutativity. Okay. Multiplication is commutative for the set of rational numbers. Commutativity for multiplication. Right. Next, in the third question, you have minus 19 by 29 into 29 by minus 19 equal to 1. This, by simplification, you know that it is equal to 1. But what is the property here that we are using? This is called something we didn't discuss in our chapter. This is multiplicative inverse. Okay, this is multiplicative inverse. Now what do I mean by this inverse? What rational number should be multiplied to a given rational number in order to get the multiplicative identity? Okay, so the answer is 1 by a, and that is the concept of multiplicative inverse whenever a is not equal to 0. So for a equal to 0, we do not have a multiplicative inverse. For any other rational number, 1 by a is the multiplicative inverse for the given rational number a. Okay. Now second question, tell what property allows you to compute 1 by 3 into 6 into 4 by 3 is equal to 1 by 3 into 6 into 4 by 3. Now what are we doing here? We are shifting the placement of these brackets. First I have A operation, B operation, C, and then I am writing it as A operation, B operation, C. We have seen that this is nothing but the associativity for multiplication, right? So what is the property here? Associativity. And I am talking about the operation multiplication. Okay. Next question. The product of two rational numbers is always a dash. Now you know that rational numbers are closed under multiplication, right? So it is always a rational number again. The product of two rational numbers is always a rational number. So with this we complete the exercise that's been given to us, and they have given us a quick recap of what we have learned. Okay, the closure property, commutative, associative, additive and multiplicative identity, distributive property for addition and subtraction, and then you have this, the idea of mean helps us to find rational numbers between any two given rational numbers. Okay, so with this we come to the end of our topic, chapter 1, which is rational numbers in NCERT textbook class 8. In the next video I am going to start the second chapter, right, which is the linear equations in one variable, right? So I am going to start the chapter linear equations in one variable.